Bonjour, konnichiwa, hello, and welcome to Space Codesign's online broadcast of our presentation from the 2014 ARM Technology Symposium Japan. We're doing this for the benefit of those who weren't able to attend the event in Tokyo, but if you did, here's a refresher for you. Our presentation will be on ESL and hardware-software co-design for rapid development of SoC embedded systems. For those of you who saw our DAC 2014 presentation, this may sound familiar, but let me reassure you there will be about 10% of the content that is new and updated from the San Francisco event. So please stay with us and let's go. So to put everything in context on the problem we're dealing with, electronic gadgets like smartphones, GPS, and tablets have quickly become a part of our lives, and it's hard to imagine living without them. But take a moment to consider that these devices are complex systems of hardware and software that must work well together, an ever-growing challenge to electronics firms who create them. Short product life cycles put severe limits on development time and cost, so these companies are hitting the wall on productivity. Product development times are now approaching or even exceeding the market life cycle of many products. So it's important that these electronic systems are designed correctly. It's not just in terms of money cost. For example, TI once telling a synopsis in their monthly newsletter that if one of their OMAP chips come back from First Silicon dead on arrival, it could cost them up to $3 million to do a respin. It's also costly in terms of time, because the added time in your product development cycle will cause you to be late to market. At Space Codesign, our technology is called Space Studio, and it's the next generation in ESL or electronic system level design technology. Space Studio is one of the few design platforms that can take you through all three stages of algorithm, architecture, and implementation. Our focus is on architectural design exploration with innovations that support hardware-software partitioning following a hardware-software co-design methodology. Space Studio is focused on system architects, but it really provides a platform for the architects to interact with software developers and hardware designers. To appreciate the benefits of using Space Studio, let's first look at the traditional workflow, which is very centered on hardware development. Hardware and software is developed on separate parallel paths. The software development usually has to wait until a minimum viable hardware design prototype appears for coding to start. Eventually, a few weeks, maybe a couple of months later, the hardware and the software is then integrated, and that's a risky step because often the software must be modified in order to run on the given hardware. And if that doesn't work, the hardware has to be re-engineered, which introduces a long loop in terms of product development time, and one that introduces the real risks of being late to market. The hardware prototype could come in either traditional hardware development systems, such as FPGA prototyping or emulation, or in the form of virtual prototypes, which has become a very popular approach in the last decade. But either way, using the traditional hardware prototype or taking advantage of the virtual prototypes earlier in the design cycle, we're still following the same two-track design methodology. Now, a century ago, in transportation, pioneers like Henry Ford, who once said if he had asked his customers what they wanted, they would have said faster horses. But the automotive pioneers presented a new paradigm for transportation, one that has literally changed the course of human history. So how can we do electronic systems development for embedded applications in a different and better way? Well, Space Studio's technology is one that enables you to follow an agile workflow. So the integration is immediate because you're creating the hardware and the software at the same time, simultaneously. That is enabled by innovations in Space Studio that allow you to retarget functions in your embedded application for either hardware or software implementation without recoding. That way, along with an electronic system level approach that provides fast, high-level simulation, you can do rapid virtual prototyping and analysis of your design to quickly converge upon an ideal candidate. This agile workflow is one that allows you to do rapid design exploration. Within Space Studio, we can support models with different levels of timing information, depending on which stage you are in your design. Early on, when you're dealing with a functional specification, or what some people like to call an algorithm, you want to validate that the behavior of the algorithm is correct, so you'd be using untimed or loosely timed models. Once you've determined the correctness of the behavior and you're satisfied with that, you then move on to the architecture exploration stage, where you start introducing details about processors, buses, peripherals, memories, etc. And with these additional details, you also have additional information on timing details. And so the modeling level then increases to what's called, from loosely timed to what's called approximately timed and cycle accurate. Eventually you will reach the RTL implementation phase. So RTL is not out of the picture. The only difference is that by the time you reach the RTL stage using our approach, you have already done a rapid design exploration to converge upon an architecture that gives you an optimal design. So that's in contrast to the traditional approach where you start at RTL and you maybe come up with 1, 2, if you're lucky, maybe 3 candidates to choose from before you have to commit to implementation. In the architecture phase, of course, you will be introducing details on processors that you'll be using in your architecture, and any functions that are in software will be running on these processors. So for processor models, in this case focused on ARM, given the event, Space Studio supports initially the ARM Cortex-A9 in a dual-core configuration, and we chose the dual-core because it has been the most popular wireless core out in the market, and it's also the core that's featured in the flagship programmable devices that come from Xilinx and Altera. In terms of sources of models that we support the ARM fast models, which come from ARM directly, or the QEMU open source processor emulator. So, some of the advantages and benefits of using the Space Studio technology are that you can pursue rapid system design by taking advantage of electronic system level technology and following a hardware-software co-design methodology, a methodology that's enabled by innovations that allow you to retarget the same function to either hardware or software implementation without recoding. For each candidate architecture, as you run a simulation, you can gather a data log of all the transactions that take place during the events, and use that data log to conduct performance analysis. From there, you can determine which candidate fulfills your requirements in terms of performance, and then once you've found successful candidates, go to the next phase of comparing them in terms of their power consumption and silicon area usage. Rather than reinvent the wheel in those technologies, Space Studio interfaces to industry standard tools, such as the ones available from the Xilinx toolkit, if you happen to be using their devices, and then later on to other technologies. Right now, out of the box, Space Studio can go to an FPGA implementation in the Xilinx domain, and we feel we can also do Altera using the same API, but we have not implemented that yet. So with FPGA implementation out of the box, you can take advantage of Space Studio to either do physical prototyping, especially if you're doing ASIC SoCs, or if your final product makes use of FPGAs, your final candidate is the one that will appear in your final release. However, if you're going to ASIC, the virtual prototype that drives the FPGA prototyping is the one that you can use as a guide to your RTL implementation. We've mentioned a couple of times that a key innovation in Space Studio is technology that supports hardware-software partitioning by retargeting the same models for either hardware or software implementation. And as an example, in this slide, we'd like to show you a before and after picture of a Motion JPEG implementation where the Motion JPEG is split into 5 functions, where on the left side, in the before picture, we have the 5 functions distributed as 2 functions on the first processor and 3 on the second. But this configuration, this candidate architecture, is not running fast enough. So the first way we might try to accelerate this this design would be to, let's say, take the IDCT, inverse discrete cosine transform, take it from software and retarget it to hardware. And in the user experience in Space Studio, it is reflected in a drag and drop mechanism where we select the IDCT, drag it onto the AXI bus, and then in the after picture on the right, the IDCT will then show up as a hardware coprocessor in the new architecture. So take this candidate, compile it, simulate it, gather a data log using our non-intrusive monitoring technology, and then do a performance analysis on this candidate and see if it fulfills your requirements. If not, continue to do design exploration by moving modules, let's say, between processors and from hardware to software to hardware, vice versa. Now, as you're converging upon a candidate, you may find that there may be issues in the interaction between modules that happen, some that happen to be in hardware, some that happen to be in software. Well, another innovation that we have in Space Studio is one where the hardware and the software can be debugged in the same engine under a single umbrella non-stop. This is important because the current state of the art involves using 2 engines. One for the hardware implementation, since ESL was originally conceived for hardware development, and then a software development and debug platform communicating with the hardware platform. So on the software side, you would be debugging the software code as it runs on the target hardware. But if you make modifications to the hardware part of the design, you will then have to stop, modify, recompile the hardware, relaunch the hardware simulation engine, and then reconnect it to the software. In the case of Space Studio, you don't have to do that. And we'll pause for a quick demo just to show you that. So we'll now go to Space Studio, bring this full size. So this is a JPEG, regular JPEG implementation where we have in the red modules 4 hardware modules sitting on a common channel, which happens to be an AXI interconnect network. And then on a microblaze processor, we have 2 other processors or tasks for the for the JPEG running under the Micro C operating system. So we want to do hardware-software co-debug, and this happens under the same engine, not 2. So we call the hardware-software co-debugging. And this just notices that some of the files are older than the start of our session. Because we're Eclipse-based, the perspective will change. So this is a debug perspective, and right now we're starting with just the hardware part. And the inverse quantization, in this example, we have placed a breakpoint at line 166, where the inverse quantization and zigzag talks to the Huffman decoder, which is software on the processor. So this is the hardware platform, and we first start the hardware simulation, which also enables the instruction set simulator, the model for the processor on which the software is going to be run. So you may have noticed that we now have more tabs here in the debug area, including tabs for the software components, or rather the functions targeted for software, the extraction, and the Huffman decoder. And in the Huffman decoder, we've put a breakpoint previously, in a previous session, at line 398, where the Huffman decoding writes data to the inverse quantization and zigzag. So as we proceed, stopping at these breakpoints, in this example we're doing sort of this ping-ponging back and forth between the inverse quantization reading from the Huffman decoder process, then to the Huffman decoding process in software, writing data that then goes to the inverse quantization and zigzag hardware. Now, even a simple example like this is one where you may encounter in the real world, because you may be finding that the data going from one module to the other is not coming out in the correct form. So we can, let's say, walk backwards and debug and figure out, okay, where did I go wrong packaging the data structure, or afterward, if it happens that the data is being transmitted correctly, what's happening afterward? Am I decomposing the data out of the message packet incorrectly? So this is back and forth between the hardware and software. You can do it interactively, non-stop, and under this, in a single engine, not two engines, where you will have to stop to recompile and restart the hardware portion if you make modifications there. And that's all we really wanted to show you here in today's demo. But we hope you can appreciate, just from the 2 minutes that we spent on that basically we're doing non-stop single engine debug. So space co-design integrated into your flow would be positioned after you create an embedded application, a C++ specification that you may develop by hand or create in tools such as MATLAB, Bridgepoint from Mentor Graphics, or CoFluent, which is now an Intel-owned technology. During the C++, and also we can put a System C wrapper around that, because System C really is just a C++ library. And then go through these steps of algorithm architecture, and then for your promising candidates implementation, and then from there drive a co-synthesis process where some portions may be mapped to reusable IP, either in libraries or reused components. New modules for hardware may be put through high-level synthesis, and then any functions that are targeted for software executables will then be compiled along with the necessary support files, make files, linker scripts, etc., and everything comes together in your embedded SoC application. A specific example would be a Xilinx-based flow, where Space Studio acts as a design creation front end to Xilinx's Vivado flow. Now in Vivado, of course, you can assemble designs, and then burn them to an FPGA, take it to the lab, and then test it. But the value added that we provide is that in using virtual platform technology, you can explore your candidates before you go into the Vivado process. And then rather than go through a lengthy lab-based hardware validation, you will have a quality design which you can take into the lab, and with any luck that will be your very first and only need to make use of the lab step in your development flow. And with Space Studio, you will be working in an ecosystem of industry standard technologies. We've talked already about the processor models that we make use of. We take advantage of the QEMU open source model emulation technology, as well as the ARM fast models technology from ARM itself. We support different operating systems such as Micrium's Micro-C and also embedded Linux. We support industry standards such as IEEE 1666, which encompasses the System C library and TLM2 standardized interface, also IPExact, which is metadata to describe your intellectual property. We partner with different high-level synthesis tools rather than reinvent the wheel. So high-level synthesis tools from Xilinx, from Forte, which is now part of Cadence, and also we've started working with NEC's Cyber Workbench team. Right now we go out of the box to FPGA, but that doesn't prevent you from using our tool to go to ASIC as well. If you take advantage of the FPGA as a prototyping step and then take the virtual prototype to use as a guide for your ASIC implementation. And with that, thank you very much. Please contact us if you're interested. Please take advantage of this YouTube channel where you're probably watching this video today. Look at our other videos and also visit our website, take advantage of our resources section, and download some of our white papers, such as a case study that we made where one of our colleagues for Motion JPEG implementation was able to look at about 24 examples over a 2-day period before finding an ideal candidate to implement based on some constraints that he was given. And so with that, thank you very much, and we hope to talk to you soon. Bye-bye. Au revoir.